A very good evening to everyone. I am Sonal Katyal and you are watching India Science.
ಇಲ್ಲೇ ಹೊರಟದ್ದು ಇಲ್ಲಲ್ಲ ನೋ there.
Employed a diverse media to communicate maths and science like cartoons, sketching, puppetry, modeling, origami, and toys. He even holds a Limca Book of Record in origami. Today he brings the science hidden in trains, shoelaces, and magic square. We welcome you, sir. Namaste.
Thank you. Namaste.
The stage is yours, sir. Please tell us how we can, use science in turning of trains, tying of shoelaces, and etc.
Yeah, I am VSS Sastry. I am from Kolar. So this webinar, is about the mathematics, in very strange places where when I went, in search of it. For example, what mathematics has to do with shoelaces? What mathematics has to do with the turning of the trines? And also what mathematics has to do in the shops and the establishments, in the bazaars, where we find in every shop a small kind of one yantra, one kind of a Kubera yantra, Lakshmi yantra, something like that, written on a copper sheet and hung over there and worshipped daily or once in a week, by the people. So this is about that. So shall we start? So now maths of the turning trines. Turning a running train is very difficult because it will be so long, more so because it has no gearbox. The piston is directly attached to the turning wheels. Indian Railways, which has got its own history of about more than 200 years as of now, has used mathematics in three locations in India, maybe more, but I have found only three to turn these trains. So look at this train. This is the famous train. It is also called as Darjeeling train. So for the members of my generation, 30 years ago, 30, 35 years ago, there was a beautiful film called Aradhana, in which Sharmila Tagore and Rajesh Khanna had acted. And it was in this very place with this train, there was a beautiful song called Mere Sapunon Ki Rani Kab Aayegi Tu. Okay, that being the case, this is the famous train. This is also train, which was started in 1879. Not only that, as of now, it is a UNESCO World Heritage. This particular train starts from Jalpaiguri to Darjeeling. So Jalpaiguri is hardly about 100 meters above the sea level or 328 feet above the sea level. It goes up to 2,200 meters, that is 7,218 feet. In fact, the highest railway station being, Ghum. So this running between Darjeeling and Jalpaiguri, train has to go up to 3,000 feet, and this journey is not smooth. The train has to go up, down, and make lots of twists and turns. And added to this is the weather, which changes continuously at the wink of an eye. It is like this. Most of the times, the train has to go through this kind of a foggy weather. Look at this. Look at the mountains, on the left and right. The train has to go in between those kind of valleys. Look at this terrain. It is a kind of a zigzag terrain. The train has to cross this kind of a zigzag terrains. And this is the Ghum station, which is the highest station among Indian railways. So, in fact, I can show you. So this one, the plaque, here it declares that this is the highest station in India. So this being the case, you may also know the track of the train. See, look at the way the track of the train is. There's lots of twists, turns, going up or down, etc. Starting from this point, it just meanders, like a river and goes to Darjeeling. And this is that Gum station. This is the highest station. Okay, that being the case, these twists and turns make the journey tedious for any driver, but make the journey enjoyable to the passengers. That's why this particular train is always, overbooked. In fact, it takes, I am told, more than 3 to 4 months, of a waiting period to book for this train. Okay, with all these things, considered, there is also another special point. It is called as, agony point. What is the kind of agony here? Look at this. The train, from here, it goes, round, 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 makes a large kind of a circle and comes to the same point and goes like this. That means to say, the train, actually, has to go come over here, take a left turn and go. This is that 90 degrees turn. It cannot take 90 degrees turn. That's why it goes, round, round like this, make a circle. That means to say the train is made to go around a circle 360 degrees, again comes to the same point and then goes. Those the train, when it goes up like this, it is very, very slow. In fact, the crossing at the same point at 5 miles per hour speed. That's why it is agony point. All this to make the train to turn 90 degrees. To make the train turn at this angle, they have to make the train to go in a circle. That means train makes a 360 degrees turn to take a 90 degrees turn, actually. So that's how, railways, have solved the problem. But this kind of a turning the train is different, at Mysore Bangalore road, and railways have a different problem, here. They have to turn the train engine at 180 degrees. Look at the geometry. So what happens is this. The Bangalore station, the problem is different because the train arrives from Mysore. It has to go back again to Mysore, but there is no space to make a big circular path as in agony point. So they would drag this engine on a circular platform and then turn this platform half around. The engine there turns towards Mysore. Then they attach this engine to train the turn and then it goes to Mysore. It is like this. The turntable is like this. In fact, the engine is brought on this turntable. This entire turntable is turned and then it goes. Let us see in a drawing what it is like. Madam, you have to. Madam, I am sharing it. Okay, right. So this is how it looks. So the train here, the train here, just have a look. The train here, it comes over here. The engine comes over here. It just goes there. It is made to come on the table like this. The entire table is turned. Look at the face of the engine. It is towards Mysore. Then it goes, take a turn and goes away. I will show you again what happens. So from this Mysore the engine comes. It is made to stand on the platform. Look at the face of the engine. So it is the turntable is turned like this. So the face of the engine turns towards Mysore. Then the engine goes and joins the train. So that's how they do it. In fact, the problem is solved. The problem is solved by putting the train engine on this platform and turning this platform itself. In fact, this kind of a platform turning is used in many places in the world. This platform at Nuremberg, you can see that at Nuremberg, it has got so many trains. Pointer options, laser, yeah. Look here, there are so many engines and there is only a single platform and it is accommodated to go to the routes like this. All these engines go different routes like this. That's so for this problem of turning the train towards Mysore, the up to 180 degrees, the solution what the people use is to make it kind of a turntable like this and turn the table itself to 180 degrees. So to turn the train at 180 degrees, railways have used a turntable. And railways have more rural stations in remote areas. One such rural station is at Kolar, which is my town. Here also railways have a train turning problem. So this is the kind of a rural station, and this has got a single platform, like this, and there is no much space, to erect the turntable or to make a circular path, as in agony point, etc. So what these people use is something different. So let us see. At this point, station at Kolar, training is coming from Bangarpet station, and it has to go back to the same station. There is no space to provide a loop path to turn the train, nor there is a turntable to make a turn. So the railways have used a geometrical theorem of a triangle to turn the train. Is it not strange, like this? So we all know the internal
Sir,
angle. Yeah,
sir, can
yes,
you please bring the PPT back? Actually, it's not shared right now. Yeah,
yes. One
yeah,
minute, 1 minute.
yeah. Now it's fine. Thank you.
Is it coming now?
Uh, give us a second.
Is it coming now?
Give us a second. This technology thing, the new technology area and its glitches. Give us a minute. Uh, 'So can you try sharing it again?
Yes, I will. 1 minute, I'm sharing.
So you may go ahead.
Yeah. So, so everybody is seeing this. Okay.
So actually, right now we see your file manager. Has the PPT opened on your?
Yes, 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 yes. Which is open.
Okay. Sir, if you close your shared screen and start again with the PPT, I think then it will work.
Yes, madam. Is it working?
No, sir. Agony point of our session. Can
Okay.
you, yeah, maybe if you click on share screen and then
Okay.
stop all the share that your current share, you close that and you start a new screen share.
Right, madam. Yes, it must be coming now.
It's okay, sir. Cool. You can use
Right,
the
right,
slideshow mode.
right, madam.
Okay. Thank you, sir. Sorry for the inconvenience,
Right, right.
everyone.
Okay, okay. So I was here. Yes, I was here. So railways,
Yes.
have more rural stations, in remote areas. One such rural station is at Kolar, which is my town. So here also railways have the same problem of turning the train. So this is any kind of a rural station. Okay, so this has got usually one platform, and no space at all, for a turntable or something like that. So this station at Kolar training is coming from Bangarpet station and it has to go back. There is no space to provide a loop path to turn the train, nor there is a turntable to make a turn. So the railways have used a geometrical theorem of a triangle to turn the train. So you know very well that the internal angles of a triangle are 180 degrees. But the external angles of a triangle add up to 360 degrees. In the path laid out at Kolar, the train coming from Bangarpet goes from point to point on the vertices of a triangle so that it covers all the external angles, thereby turning its face to Bangarpet. It is like this. You are seeing a triangle, here. You are seeing a triangle, isn't it? You are seeing a triangle, and I have to show you, how it is work. So it is from this kind of a triangle, point A, point A. So the train comes, from this triangle point A. Then this is the external angle. So it goes, like this to another vertex. Then it comes back. Then it goes to the another vertex here, and then it takes a turn. So with this image, you will not be sure of how it turns. So I will show you a drawing, here. Madam, I have to show the drawing. So you are able to see this, isn't it? So this is the kind of a triangle. So look what happens, here. This is a triangle. This is A, B, and also C. This is the internal angle of the triangle A. This is another angle. This is another angle. Total A, B, C, the internal angles are 180 degrees. But this triangle also has an external angle. So this is the external angle A. This is the external angle C. And this is the external angle B. This is the external angle A. This is the external angle C. This is the external angle. This is the external angle B. So let us see what happens. This engine, it comes, from here, from Bangarpet to the point A. It covers this external angle, goes up, like this to the point C, vertex C. So it covers, this angle, external angle. Then it comes back, like this. And it goes back, like this, covers this external angle and goes back, like this. See, it entered the the triangle, with this face, here. It goes up, and turns like this. Look at the face. It has turned, already. So that's how, by covering the external angles A, C, and also B, the train, is turning towards Bangarpet. So that's how, they have used the theorem. Let us go to the PPT now. So we have to go to the PPT.
So you will have to share the PPT again.
Yeah, yes, I am sharing. Yes.
It's the
So
wrong
this,
window. It's the sorry, sir. It's the wrong window again. The same thing happened previously, no? So if you open the PPT and then you share your screen.
I think I am looking at my screen. It may come, right? Okay, Mercy. I will do that.
Yeah, you close the screen sharing, open the PPT, and then you may
Okay.
share it. And I think that will work.
Is it okay now?
Yeah, it's fine. Thank you, sir.
Yeah, yeah, yeah. So, we were at this. So I have shown you, the triangle, how the external angles, from the outside, the A, B, C, are covered. And also I have shown you how, the train engine, gets its face, turned. So now, let us sum up. We are having, three problems. One at the mountain station, Darjeeling. So the agony point, there, the problem was 90 degrees turn. So the railways, make the train to go 360 degrees and cross the same point over a bridge. So at Bangalore, Mysore, at Bangalore station, the problem for the railways is turn the train at 180 degrees. So they put it, on the platform and turn the platform itself at the turntable 180 degrees. So at Kolar, where these kind of a large areas, of like making us into a circle as agony point is not there, neither, there is a turntable. They use a geometrical theorem that the internal angles of the triangle are 180 degrees and also the external angle of the triangles are 360 degrees. 360 degrees means as if to go into a circle. So that's how in three different stations, they had, three different problems and three different solutions, they got all based on middle school level mathematics. And also a forgotten theorem of external angles of a triangle are equal to 360 degrees. Is it not fascinating to see that a kind of a strange place, like, railways, this kind of a mathematics is used? Hello? Now let us see in what other ways, these are there. So I also, told you regarding, the different areas, where I searched that mathematics, is there in strange places. Shoelaces is one of that kind. Shoelaces, everybody, wears a shoe, especially the winter is approaching now, and everybody, wears a shoe. So, and shoe means there is definitely, there is definitely a shoelace. Am I on the screen, madam?
Yeah, you are at the screen, and whenever you are ready to share the PPT, you can start sharing again.
Okay, I would like to share now. Okay, right?
Can you start the share screen process again, please, sir?
Let us see. Is it okay? Is it coming there?
Uh, just give us a second. It's loading.
It may be streaming.
No, sir, not yet. Can you try again, please? The same
Yes, I will.
procedure.
Yes, I will. I will. I will. I will. Right.
And maybe when it's all done and when the PPT is on the screen, let's try
Yes.
without clicking the stop sharing screen button next time. So I think then it will stay.
Uh-huh. Really. So you are able to see now?
Yes, it's loading. Just give us a second. No, it's again the wrong window. So it should first open and then it should be shared.
Yeah. Yes, yes, yes. Okay, madam.
Till then, maybe our viewers can think about all the shoelaces they have tied in their
Yeah.
life and think about
Yes.
all the ways and maths could be involved in this. In fact, a research paper was once published sometime in 2017 about what is the science behind opening of shoelaces.
You are able to see, madam.
Uh, it's not loading yet. No, no, not yet, sir.
So what to do?
Maybe can you stop all the screen share on your end and then open your
Yes.
PPT and then share the screen again
Okay, madam.
and then go to the PPT.
So I have opened the PPT now.
Okay, and now start the screen sharing again, a fresh one.
Yeah.
It hasn't come yet.
Now it should come.
Um,
Has it come now?
no, no,
It should.
it hasn't come yet. Now it has come. Now it has come. The shoes
Yeah.
ran away with the laces and they are back. Thank you so much for the
Okay, okay.
patience, everyone. Okay.
So these are the shoes, normal shoes which everybody wears, especially the students, when they go to the school. Okay, this is a kind of a normal lacing. So look at here. Normal lacing means this is the kind of a least difficult kind of a lacing. So all the kind of a buckles are here. Okay, all the kind of holes are here. Straight away now it is done. It is passed in a zigzag. That's how it is done. So this is not the only thing. There are very many types of lacing, the shoe. For example, this is the lattice. This is the hidden knot. This is the ladder. This is the checkerboard. This is the loop back, display, double back, zipper, sawtooth, so riding bow, so many things. Okay, let me also show something else. Let us have a closer look at this. Look, these are all different kinds of methods of lacing the shoe. This is called sawtooth, shoe store, parallel, train track, military, crusade, staircase, crisscross. See how many types of shoelaces are there. But one thing is true. Every kind of a shoelace should be very very easy to untie, because tying the shoelace may take time, but untying the shoe must be very easy. Guess in how many ways you can tie your shoelaces, or in how many easiest ways you can untie. It's actually there are 51 ways of doing that. Is it not strange? Okay, let us go back to when the man was using this kind of a shoe and also shoelacing. The records show that Arne shoe, the picture what you are seeing here, is created 3500 BC. So look, from since then 5000 years almost we have been lacing the shoe and also using the shoe. Okay, what is to do? It is to do with mathematics. Yes, there is a connection. So look at this man. He is called Frederick Gauss. He is a mathematician. In fact, in our textbooks, we find his photograph. Not only that, we also find the kind of a bell curve associated with his name. This is also known as Gaussian curve, the normal curve, normal distribution, etc. This occurs, universally, everywhere. That's how Gauss is remembered. And Gauss, as a mathematician, looked to this kind of a shoelaces, shoe patterns in a peculiar mathematician's way. Okay, let us start with this. So this is a kind of a normal kind of a shoelacing. So, but how Gauss looks at it? Gauss Because he is a mathematician, he names it x1, x2, x3. Those days start from here and go to y1, y2, y3, etc. And we think, the normal people, it is only a kind of a rectangle, like this. But mathematician like Gauss, they look, this x1, y1, x2, y2, x3, y3 as connecting not these holes. They see this polygon with many vertices, like a regular pentagon, irregular pentagon, concave octagon, irregular hexagon, etc. They look at it, the things, like this. These are the, imagine, these are the kinds of the holes connected, like this, through one loop. Okay. Yes, Gauss formula for Shoelace theorem is there. The Shoelace formula or Shoelace algorithm, also known as Gauss's area formula, is a mathematical algorithm to determine the area of a simple polygon whose vertices are described by the Cartesian coordinates, etc. So again, let me go back. So this particular area, this particular kind of a pattern, Gauss, looks at kind of a area problem. So what he is concerned is that the between these points x1, y1, y2, x2, x3, y3, which he imagines like an irregular kind of a polygon, he thinks that the area to calculate the area, some kind of a technique has to be used. I told you about the irregular polygon like this. Look at the shoe. This kind of a crisscrossing, what they have done with the holes. I told you these holes, he imagines like the vertices A, B, C, D, E of a irregular polygon. So his concern is that what is the kind of between these holes A, E, D, C, B, etc. Here is a simple, irregular polygon I have shown. Imagine this, abstract this, to more. So what is the kind of an area, like this? So he starts from here, A, B, C, D, E, and each are having coordinates. This is A is 2, 7, B is 10, 1, this is 8, 6, 11, 7, 7, 10. He lists, like this. So what he does, to calculate. So look at the crossing, what we have done, here, lacing. Similarly, what he does is, he makes, 2 into 1, 10 into 6, 8 into 7, 11 into 10. Similarly, 7 into 10, 1 into 8, 6 into 11, 7 into 7. Just like, the crisscrossing of the shoelaces. Then he calculates their product and the sum and takes, one bigger, from the lower. Then you get the area. Look how he integrates the shoelace pattern with the abstract polygon and starts multiplying, just like the shoelace crosses, like this, and then does it. That's how mathematicians think. Shoelace problem, which Gauss, has done it, is a very, very important advance. It also shows you how mathematicians, think. And again, I want to go back to this particular pattern. He imagines like an irregular polygon. Next, he devises a cross multiplication like this and gets the area. Okay, this being the mathematician's case, there is also something else interesting regarding the shoelaces. Of course, this is the formula on which he gives. Because it is a polygon of very many sets, he goes up to n. Okay, now, how shoelace pattern was used in history? So remember this man? He is Mountbatten, the last viceroy of India and the first governor general, of India. So in the Second World War, when the Japanese, overran Singapore, Indonesia, Malaysia, etc., Mountbatten was a commander, for the British 8th Army. What is that British 8th Army? They were just the army consolidated out of Indian subcontinent. That means that we are had, lot of princely states, etc. And they also included, this Nepal, the Gurkhas. Even today, we are having, a Gurkha regiment in our military forces. So these Gurkhas were were used, for the liberation of Singapore. But unfortunately, the Gurkhas, as well as their enemy, the Japanese, they almost look alike because their features are Mongoloid features. They look alike. So, but Gurkhas also had another problem. They were not educated enough. So, what Mountbatten did was he employed these shoelaces. What is it about? Okay, because the military has a discipline. Their uniform is same, their hats are same, their shoelacing is also same. So this is how Indians had their shoelaces. This is how Japanese had their shoelaces. So Mountbatten told the Gurkhas to identify whether he is our man or the enemy. Look to the shoe and then shoot. That's how the shoelaces had that kind of a history of shooting in Singapore. So is it not fascinating that this kind of shoelaces have such a history and also connected to mathematics, through the Gauss shoelace theorem. So let us go for next item.
What is the next story about, sir?
Yes, madam. Yes, madam. There is another PPT. Okay. Yes, I am opening it. Yes, you are able to see.
Yes. Perfect.
Yeah, yes. So the magic squares, in Indian culture. So magic squares, are quite fascinating. So magic squares are part and parcel of Indian folklore, in fact. In any retail shop, all over India, in the bazaars of India, we can always see a framed metal foil containing magic chants, some kind of a mantra, and also a magic square. The shop owners give a lot of respect to this particular frame and worship it once a week. Usually, it is on Tuesdays and Fridays. Those frames, metal frames, look like this. So this is Sampurna Kubera Lakshmi Yantra. Sampurna Kubera Lakshmi Yantra. So as well as this Lakshmi Yantra and Kubera Yantra, put together. Usually you see these kind of figures. So what is there in this some Lakshmi Yantram? Look to the particular numbers here. I have written it here. This is 816357492. It is placed, this entire yantra is placed in office, home, or shop, worshipped for wealth, fame, prosperity, success, etc.
Sir, sir,
Yes.
sorry to pause you. We will. I think you will have to share the screen.
Okay.
Yeah, the screen is actually not in slideshow mode, so we are still stuck on the title slide.
Oh, really?
Yeah.
You are able to see.
Let us check. No, sir.
Wait a bit, madam. I will open it again.
Yeah, if you open it, and I think there was that enable editing button, and then you go to the slideshow, and then you start from the beginning.
Yes, madam. Enable. What is that button, madam?
Yeah, the one that was showing. Can you access the slideshow button now? The one
Yes.
on the top. If you click on slideshow, then from the beginning.
Yes. Is it coming?
Yes, and then you click from beginning. From beginning.
Yes. Yeah.
Yes.
You are getting it.
No. Can you click this enable editing button, which you can see just under that bulb that says "Tell me what you want to do."
Enable button, is not. I am
Enable
unable to.
editing. You can see this yellow line that says protected view, just a bit
Ah,
top.
yes. Yes.
Yeah.
Enable. But
Yeah.
yes.
Yeah.
Yes. Yes.
Just click this enable editing,
Yeah.
and your and then you go to slideshow.
Now.
Oh, it actually went away. You'll have to share the screen again. Keep the PPT as it is, and then just stop the screen share and start the screen share again.
Okay. Yes. Now
Um, yes, it is loading.
it should be no. Is it
Yeah,
there?
it's there.
Yeah.
Yeah,
So I
it's
have to
there.
start from the beginning.
Yeah, I think your window is Is it maximized? Can you see the whole of the PPT on
Yes.
your
Hold.
screen?
Hold. Hold. Yes. 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 I can.
Okay. Okay, please continue, sir.
Yeah. So this is the commonly screen, magic squares, and the yantras, in the shops and etc. It contains, magic squares, like this. So usually, this is the magic square: 816, 357, and 492. It is here, you see. And also for Kubera Yantram, also, here is a magic square. It has got, 27, 20, 25. In fact, it is the same, here 19, added. 19 plus 8 is 27. 19 plus 1 is 20. 19 plus 6 is 25. 19 plus 7 is 26, etc. So this Kubera Yantram is also, is hung, in usually northeast or east facing direction in office, etc. And Lord Kubera's lucky number is 72. What is that 72? When you add, this 27, 20, 25, you get, 72. Similarly here, 8, 1, 6 is 15. 6, 7, 2 is 15. 2, 5, 8 is 15. 4, 5, 6 is 15. That's why it is called as magic square. There is nothing in a magic extra here except that straight horizontally, vertically, diagonally, these add up to the same number. Here it is 72, here it is 15. So there is also another kind of a yantram, which is hung in shops, etc. That is called as, Navagraha yantram. Remember this? It is the same what you saw here. 816, 357, 492. It is the same here. It is written in reverse. 816, 357, 492. Okay, what about here? In fact, 2 is added. 6 plus 2, 1 plus 2, 8 plus 2, etc. What about here? 1 is added. 6 plus 1, 1 plus 1, 8 plus 1, etc. How about here? This is 5 is added. 6 plus 5, 1 plus 5, 8 plus 5, etc. So like this, E1 from 1 to 9, everything is added. 1 to 8, everything is added. Including this, it becomes, 9 magic squares. For that, they call it as Mercury magic square, Venus magic square, Moon magic square, Mars magic square, Rahu, Saturn, Ketu, Jupiter, etc. And this being, the Sun. Okay, this is the principal magic square. What is principal about it? In fact, this is the first magic square discovered anywhere, or that there is a story. So during 650 BC, times of the great floods, in China, Emperor Yu, his name was Emperor Yu, he was walking along a river. Its name was Lo. While the king, tried to channel the water out to the sea, a turtle emerged from the river. Its shell had a unique pattern of 45 circular dots arranged in a 3 and 3 grid. The arrangement was such that the sum of the numbers in each row, column, diagonal was the same, 15. In fact, this, I have written, there, 816, 357, 492. As the legend goes, the interpretation of this grid pattern guided the people to control the river flow, thereby protecting themselves from the flood. In fact, this 3 and 3 grid is popularly known as Lo Shu Magic Square. Nowadays, Feng Shui, a new religious system started in China, is based upon this Lo Shu. It is also very much popular in India. Every normal magic square of order 3 is obtained the Lo Shu by rotation, reflection, etc. For example, here, what is happening? This is the actual magic square 816, 357, 492. This is made in a ulta 492. They write in the top 357, 816. Okay, how they get make this kind of a numbers from 1, 2, 3, 4, 5, 6, 7, 8, and 9. What is the kind of a formula they arrange it like this? There is a formula. In fact, Loshu magic square construction is like this. First, you get into three boxes. Totally, 9 boxes, 9 small squares like this. Write down numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So here, between 1 and also this 4, 2, draw a line like this. So this becomes kind of a square. That is here. What this kind of a square makes? This 1, 3, 9, and 7 is kept out. And there are 1, 2, 3, 4 open squares, non-filled squares. So what you do here is take this 7, don't put it here, jump this 5 and put it here. Similarly, 3, jump this 5 and put it here. And 9, jump this 5 and put it here. And 1, jump this 5 and put it here. So this becomes, after these kind of operations, like this. It is the same 816, 357, 492. That's what I have written here. That's how Low Shoe magic square is obtained. And in a Navagraha Yantram, that Yantram, etc., Kubera Yantram, etc., only this is manipulated. Let us see what is about that. This is called as Kubera Yantram.
Sir, sorry, I'll pause you. Can you exit the slideshow mode and just we'll just do the slides manually. If you can exit
Okay.
the slideshow mode, if you just show it here, because the screen is getting cropped
Okay.
on the right now, so now everybody
Now
can see all the steps. This is fine.
everybody can see. See, please see how Kubera Yantram
Yeah,
magic
now
square is constructed. This contains, same thing, 9 squares from 20, 21, 22, 23, 24, 25, etc. So draw this is kind of a small square, like this. So 20, 22, 28, 26 are out. These kind of open squares, are here. So 20, you put here, jumping 24. 28, jump 24, put here. 22, don't put here. You jump 24 and put here. 26, again put here. So after this, it becomes like this. So this is that Kubera Yantram, 27, 20, 25, etc. This is that Kubera Yantram. So in fact, this yantram also can be obtained, as I told you, from this low shoe magic square. Go on adding, 19, here, 19 plus 28, 19 plus 1, 19 plus 6, etc. You get, this same Kubera Yantram magic square. So these magic squares, are everywhere, in every shop, in every household, who think that this kind of a magic squares, have that kind of a magic. If you just worship them, you will get, prosperity. In fact, magic squares, are a kind of a folklore in India. They have been, with us since long. In fact, this is the magic square pillar at the temple in Purani in South India. Palani is a very famous place where Lord Subramanya is worshipped. This is from 8th century AD. On a pillar, you find, this. When I translate this, it is the same. Same thing, 816 357 492. Remember this? This is the low shoe magic square. So it is on the temple pillar from the 8th century AD. Similarly, you have on the Parshvanatha temple at Khajuraho, on a pillar, this is that kind of a figure, you get. This is called as, Chautis Yantra. What is that Chautis? Because when it is translated like this into Roman manners, it is like this. In fact, it is a magic square, 4 into 4 magic square. 7, 12, 1, 14, 2, 13, 8, 11, 16, 3, 10, 5, 9, 6, 15, 4. When you add, any column, for example, 14, 1, 12, 7, it is 34. 7, 13, 10, 4, 34. 9, 3, 8, 14. It is also 34. Not only that, 7 plus 12 plus 13 plus 2 is also 34. 13, 8, 10, 3. Also 34. 10, 5, 4, 15. This is also 34. So in 52 different ways, you can find, 34. That's why this magic square is called as, Chautisa Yantra. Though we do not know, why, what purpose, it is there in the Parshvanatha temple at Khajuraho, this especially shows that the mathematical magic squares, were extensively, in use. I will show you another example. And the Gwalior fort, there is one gate called, Market Gate. There, you find this particular magic square. So similarly, in very many of the panchangas means, this usually this religious mutts, especially in South India, produce these ephemeris, the calendars. So one such calendar is published from Shringeri Sharada Peetham in Karnataka. There you find, this one. This is continuously printed since 70 to 80 years. This is called as, Ramachakra. This is also, please remember, this is also the same thing, what you saw here, 4 by 4 magic square. Only the number 1 to 16 are arranged, in a cyclic way here. It is the same thing. So this is used, for a different purpose. For example, it is used, to predict, one's future. What do I mean by that? So whenever, let us say, when somebody, wants to go to a different place, he wants to take a yatra. So a child is called and asked, to put a finger, closing his eyes. Let us say, he will put at number 2. Then in 2, something is written, whether it is useful to you, whether it will bring, luck to you, etc. But okay, whatever it is, the mathematical content is that this is a 4 by 4 magic square. From 1 to 16 numbers are arranged in like this. Okay, I will give you, another example where this kind of a same magic square 4 by 4 used for a different purpose. Yeah, this is called as, Vastu magic square. So nowadays, for Vastu considerations are more. To construct a building, they will make, some kind of a puja and put this particular magic square, on a copper plate and put it inside, a ditch in that site and then start construction. In fact, this particular magic square is peculiar in the sense this is from a painting, like this. This is called a melancholia painting. It is written, it was etched, it is an etching on 1514. It is from Albert Dürer, a German artist and a mathematician. The engraving shows a sad winged woman here and also another angel sitting together and wailing. They are crying. We do not, it is symbolic, we do not know what for. Behind this structure here, there is a 4 by 4 magic square. The year 1514 is also written here. That's when this etching, was done. Nowadays in India, this magic square is, used for Vastu considerations. In fact, magic squares are quite popular, like this in India. This is a kind of a new avatar, you are seeing in 20th century. I will just go back. So this is the photostat copy of one old manuscript This is a leaflet from Bhadraganitam, that is the name of the book by Narayana Pandita. So it is from the time about 1710. So here you see lots of numbers, like this in beautiful lotus patterns. In fact, hexagons. In fact, this yields a total. Let me show you, how it can be written in Roman letters. See here, this is the entire circle, and from the center circle, let us start. This contains, 6 leaves. They are connected, by another kind of a curved leaves. The same kind of a pattern is here. Same circle with 6 leaves, hexagonal leaves connected. And this half circle is shared, by this circle. This is shared by this circle. This is shared by this circle. This is shared by this circle. Like this, there are 7 interlocking circles which petals, like this, 6 petals, here, 6 petals, joined together. What is the peculiarity? You add this 15 plus 6 plus 14 plus 4 plus 13 plus 5 plus 31, 47, 33, 48, 32, and 46. So totally 12. You get 294. Similarly here, you take these 6 petals and also these 6 numbers. You get 294. Anywhere you go, this 6 plus also this 6 is 294. This 6 plus also this is 294. What does it show? It shows that magic squares are the mathematical objects which are used in Indian culture in one way or the other. Somebody uses it as a talisman, somebody uses it on the pillar, somebody uses it on the Khajuraho temple, somebody uses it elsewhere for the Vastu considerations. So magic squares are the mathematical objects. The strangest thing is nobody knows that these are magic squares or mathematical objects, and they can be constructed in a time-tested time-tested magical procedure that is called as algorithm. These magical hexagons, this particular hexagon is unique in the sense this is the only magical hexagon existing in the world. But 3 by 3 the magic square you saw, low show magic square, as well as you saw this particular magic squares like this, or can be written in a particular algorithmic way. Algorithm means there is a formula to write it. So, but in the popular parlance, these are magical in the sense they give the same total. That's why these are magical. People think that they give you something extra power. That's why this have already entered into our folklore. So I have shown you 3 different areas in which mathematical objects are everywhere in India, are used in India. One is the magic squares. Next is strangest place is shoelaces. Next strangest place is the turning the train problem of Indian railways. So I think you found it very interesting. In fact, when I investigated this kind of finding mathematics everywhere in strange places, I found more than 25 different places in which magics being these magical objects or mathematical objects are used, but nobody knows about it. So today I have shared with you only 3 of my in my collection, and I hope you found it is funny and it is enjoyable because I have enjoyed the same. Thank you very much.
Thank you so much, sir, for sharing all this exciting stuff. I'm sure shoelaces would mean more to us, and the song Sapno Ki Rani will remind us of mathematics other than Sharmila Tagore. Thank you so much, and
Yeah.
I would like to thank all our viewers to join us this evening. And we have other exciting shows with V.S. Sastry ji and many other documentaries on mathematics, which are available on our free channel www.indiascience.in, which you can also access as a mobile app, which can be downloaded from Apple or Google Play Store. Thank you so much, sir, for sharing your knowledge with us, and we hope we'll have some more sessions with you in future, and we hope we'll have all of our viewers again with us. Thank you so much. Namaste, and a very happy Navratri to all.